Welcome to my world of physics.co.uk. Today I'm going to talk about my recent work entitled Quantum Entropy and Exact 4D5D Connection that you can find on our archive. In this paper, we study ADS-251 correspondence in the near horizon of five-dimensional supersymmetric black holes. According to Sen's proposal, the number of states in particular charge sector Q can be evaluated by performing a path integral of string fields on ADS2 with some Wilson line insertions. In the large charge limit, which is also the thermodynamic limit, we recover the Leyden-Bekenstein-Hawking entropy area over 4. We can use this formalism to compute systematically perturbative corrections to this result. For instance, we can compute logarithm corrections to the area formula. In some cases, we may use localization to compute the path integral exactly and try to compare it with known microscopic answers. Ultimately, we want to show that the correspondence works even for finite charges. In this case, we may prove holography. In localization, we deform the physical action by adding an exact Q term. It can be shown that the path integral does not depend on the parameter t. So in the limit, when t goes to infinity, the computation collapses on the solid points of the deformation action and possible one-loop corrections. That is, the semi-classic approximation becomes exact. Usually, the equations of motion correspond to the BPS equations. In the paper Quantum Black Holes, Localization and a Topological String, we studied this problem in the case of four-dimensional black holes. We perform localization of shell n equals to supergravity on ADS equals 2, and show that the scalars in the vector multiplets are left unfixed and have to be integrated. The renormalized action is computed to give the following form, where phi are some potentials that have to be integrated, and f is a prepotential of the theory. The quantum entropy is given by a finite dimensional integral. After considering the measure on the space of phi's, we find an impressive matching between the microscopics and macroscopics, as explained in the paper Localization and Exact Holography. In this paper, we consider five-dimensional rotating black holes, which have near-horizon geometry, which is a circle fibered over ADS2 versus 2. The fiber carries angular momentum, which from a four-dimensional point of view gives rise to a U1 gauge field. DeWitt et al. Perform a standard closed-decline reduction of the five-dimensional theory, which gives a theory on ADS2 versus 2. Here, we use five-dimensional localization to show that the path integral reduces to a finite-dimensional integral. For this, we need to consider localization in a non-rigid background. That is, we don't assume a standard closed-decline reduction. We keep all the fields off-shell as much as possible. To use localization, we need a fermionic symmetry delta that squares to a circle action. This implies that the fiber fields cannot depend on the fifth coordinates. The localization equations then follow. For the vector multiplets, the variations of the K-Gini give five-dimensional localization equations, which are new in this context. The variation of the Gravitini give four-dimensional localization equations, which were studied before in the case of ADS2 courses 2. From a 5D perspective, the localization equations look very complicated. There are a great number of fields, both from the wild and the vector multiplets, that are left unfixed. However, after field redefinition, they are the solutions found in the problem of localization on ADS2 courses 2. To compute the renormalized action, we need to add appropriate boundary terms. These Wilson lines differ from the ones computed in the case of ADS2 courses 2. In the absence of higher derivative corrections, we compute the renormalized action on the localization locus to give the following expression, where phi are some potentials that have to be integrated. After an analytic continuation, this matches with a four-dimensional renormalized action computed on ADS2 versus 2. This happens as expected. What are the unsolved problems? We need to compute the contribution from higher derivative terms. This revealed to be a technically difficult problem due in part to the presence of the terms and Gauss-Bonnet corrections in 4 dimensions. What about one-loop determinants? Since we did the computation in a partially fixed background, we don't have access to all possible fluctuations. In other words, we don't know how to construct a quantum gauge fixed action. Instead, we can use some effective measure on the space of phi's, as we did in the case of four-dimensional black holes. Thanks.